Welcome to EPG Pathshala, which is the lecture series for postgraduate architecture. The paper we are discussing is Sustainable Green Building Design, and the module we'll be delving into is Basic Principles of Passive Design Part 2. Now, moving on to passive solar heating strategies. So, the main three strategies we have seen are direct gain, thermal storage wall, sun space. You might actually wonder in a country like India, why do we need solar heating strategies? And that is one of the misconceptions most of our architects have, not only in India but even outside, that India is a hot country. Though it is predominantly true for the most part, there are lots of parts of the country that are much colder and cooler, and unfortunately our mechanical heating systems is not as advanced as the mechanical heating systems that are available in our counterpart Western countries. So, more than having passive cooling strategies adopted in our country, I feel it's more important to concentrate on solar heating strategies because it is more prevalent and more relevant in cases in our country, especially in Himachal, Delhi, and places like that in winter, where people cannot afford certain mechanical devices, and if at all they do afford those mechanical devices, they are of very poor quality and they cause a lot of accidents like fires, etc. So, passive solar heating strategies cannot be ignored even for the Indian context. So, like we were discussing, we have direct gain. Direct gain, and the first thing that we have seen, where we are making sure that in the direction of the sun we have a large glazed opening. Second is thermal storage wall, where we are encouraging the sunlight to hit a thermal storage wall where it will absorb the heat and release it gradually. Then sun space is nothing but like how a veranda was designed in hot and humid climates to keep this house cooler. A sun space is added to a colder climate house to keep the interior rooms warm. So, this space will be cool, but as this will be a thermal wall, this can be used as a buffer zone between the exterior and the interiors of the house. So, this could be a sitting area, this could be a solarium where plants are kept, any of these things can be utilized. So, if you look at the general rules for passive solar heating, conservation levels should be higher than normal levels of insulation and air tightness, distribution of solar glazing, distributed throughout the building proportional to heat loss of each zone, orientation optimum within 5 degrees of true south, glazing tilt, looking for perpendicular to sun angle in winter, although vertical efficient where lots of reflective snow cover. Number of glazing layers, if you look at that, 3 to 4 for severe climates and lesser otherwise. Night insulation and low E glazing. So, what this basically does is improves reduction of night heat losses, and it mixes both passive systems, which will increase the comfort level inside. So, if you look at this example over here, it's a classic direct gain for heat. The sun shines through the windows, strikes the exposed concrete, and this heat is this acts like a thermal mass, which is a good absorption, and when the space cools off from the concrete, the heat will radiate out to make the space warm. Now, if you look at these cross sections of spaces in these pictures, the sun heats the corridor. We saw in the previous slide as well. The sun will heat the corridor, and then once during the day when the corridor is heated, then it allows for the heat to escape to the inside spaces or the interior spaces, which is basically occupied. But what happens in the night? So, this is what happens in the night. The openings are closed, which helps the office to retain the heat till morning. So, even when you come in the morning, the space is not completely cold, but it is relatively within the comfort zone. So, if you look at the first diagram over here, this is in the daytime, and this is the example of the Aldo Leopold Center in Wisconsin, which we have even seen as a good example of sustainability. So, here you have direct heat gain. This is the sun space sort of a structure that we have. Then there is the thermal mass which takes it to the interior spaces of the office. So, now the office is warm and everything. Now, in the evenings, all the openings are shut. So what is kept warm is constantly kept warm till the next morning. How do you go about now moving to the passive strategies of cooling? This is another important thing that for our Indian context is useful, because here we have another hindrance. We have no shortage of mechanically cooling devices. That in our country there is no shortage of air conditioning, HVAC, different kinds of air conditioning, tower model, cassette, whatever it is, it's all available and in plenty. So to prevent easy option of choosing that, we need to make sure people and architects especially are aware of the different strategies available for passive cooling. So now if you look at the first tier in this case, you have heat avoidance. How do you prevent heat from getting into the building? Like we have seen in our previous slides, once the heat or light is inside, it is very difficult to control it. So the first step is to avoid the heat from entering the building. And the second step is passive cooling. Say the heat has to enter the building, obviously, because for practical reasons we cannot have a cordoned off building. So how do we go about using passive cooling techniques to cool the building? And last resort is what kind of renewable sources of energy can be used for mechanical cooling. Like we saw these solar powered air conditioning, wind powered air conditioning, cooling towers, water towers, all of these are examples of passive cooling and mechanical cooling combined. What exactly is passive cooling? As much as possible, passive cooling uses natural forces, energies and heat sinks. Since the goal is to create thermal comfort during the summer, which is the overheated period, our options are we can either cool the building by removing the heat from the building by finding a heat sink, or the second option we have is raising the comfort zone sufficiently to include high indoor temperature by increasing air velocity so that the comfort zone shifts to higher temperatures. So here there are two ways of dealing with it. We have to first identify a heat sink, which means that we can find a place where all the heat can be absorbed by. Or the next thing is, usually what happens, what is the purpose of a fan? The fan doesn't change the temperature of the room. Air conditioner changes the temperature of a room. But what a fan does is, it keeps the air in motion, which will ensure that the room is cool and comfortable. So that is what we can do. We have to play with the air velocity, create an air shaft, a stack effect or something, where we push the air into the room at a greater velocity, which will keep the place vibrant and light. So passive cooling relies on two primary strategies. First and foremost, prevent heat from getting into the building. If it does not come in, then we don't need to get rid of it. Next, using shading devices, creating a cool microclimate to discourage heat buildup, get rid of unwanted heat that comes into the building in cold and temperate climate, mainly via ventilated cooling. So what is ventilate cooling? If you look at it over here, as the name suggests, using a ventilator as a combination to a window, we can cool the building. So what does a ventilator do basically here is, it helps exhaust out the warm air and replace it from cooler air from the outside. So directing moving air across occupant skin to create convection and then evaporation. So this is achieved by wind, stack effect or even fans. So like here, that is what I told you, this is a combination of tier 2 and tier 3, where we are talking about passive cooling along with some mechanical help. It is important that these openings are not only provided but located correctly and should also be of the right size for it to work well. This is heat avoidance. This is Salt Lake City Library. You can clearly see there's a huge buffer space over here. You can see the glazing. It is such a thick glazing and the layers, and this, by the time the light that comes here has no heat component, but it is completely only daylight. Vegetation can also be used to shade the building to create a cool microclimate around the building. So you can see over here the material doesn't even matter. So you don't have to worry about an exterior finish or anything like that if you're going to have a vegetation which will completely cool the building by 2 to 3 degrees at the very least. Courtyard spaces can provide a cool, semi-private interior microclimate from which you can draw cool air into the building. This is frequently used as a strategy in our country, but again, it is very crucial that the courtyard is located at the correct space. The courtyard cannot always be punctured in the middle of a building. The courtyard has to be a transient space between the exterior and the interior, and it will act as a funnel to channelize the air into the building. Now, how do you go about reducing energy loads in daylighting? Again, we have a three-tier principle. What is our tier 1 is, how do you go about orienting and planning of a building such that you allow maximum daylight to enter the spaces. Next tier, next important thing is glare, color, reflectivity and material concerns. And finally, obviously you need to have mechanical lighting because a building has to have purpose even beyond the sunset, and even we cannot completely depend on the quality of the sun always because of seasonal changes. But you need to have efficient artificial lighting with sensors which will decide upon the usage and the number of occupants in the room. So even the energy efficient fixtures that we use add to the sustainability of the building and make sure that we do not consume much of the non-renewable resources. And another important factor which we cannot stress enough is daylighting does not equal sunlight. Daylighting is about bringing natural light into a space. Look at the Beijing National Theatre. Can you say that this place is hot and sunny, but it is completely lit by natural light? It is because of this curved glazed wall in the correct direction that is allowing the best of the natural light to enter in without having the unnecessary heat gain. Many such spaces do not want or need direct sunlight, and direct beam sunlight is about heating the space, which in most cases we want to avoid. Most cases, like I've specified, in colder climates sometimes that is what is required and we directly want to heat up the space as well as light it up. How do you differentiate between passive solar heating and daylighting? Direct sunlight is about free heat, and daylight, which is nothing but diffused sunlight, is about free light. Daylighting is environmentally advantageous because it reduces the need for electrical lighting, therefore reducing the energy needed to power the lights, reducing the heat generated from the lights, thereby reducing the cooling required for the space. So you can see they are all interconnected and have a very close-knit relationship. Lights can be used to reveal experience, and this is what a mark of a true architect is. Seattle Public Library by Rem Koolhaas. You can see how without actually adding any external features, he's created such an interesting pattern because of a shading device, because of a glazing device, and because of the daylight. So even though the space is completely naturally daylit, there is no heat gain whatsoever. This is British Museum by Norman Foster, following along the same principles. A beautiful pattern is created, and throughout the day, by the hour, this pattern will change as the sun angle keeps changing, and that's what gives this place a very unique creativity. You have a large number of buildings that treat windows as patterning devices and do not take advantage of the sun in obvious ways. If you actually look at this building over here, these windows are not even there for a purpose of serving as a window. They have actually typed out the company's name and the motto in Morse code. So all this is what we are talking about not being sustainable. It is a cool factor, it makes the building hip and cool. But how sustainable is it? This could end up being the western wall, which will bring in a lot of heat, and it's completely sealed off. All the windows are sealed, which will not let in any ventilation to come in, and even the light cannot be controlled because all the windows are in the same flat level. There is no play of spaces whatsoever. Now moving on to the next realm of sustainable design is to ensure using the correct kind of materials, or what we can otherwise refer to as sustainable materials. So again, following the same example of the Aldo Leopold Center, you can see what kind of materials are used. Materials need to be part of the initial thought process as well as from the stage it is being conceived. It should not be like the plan and the material that has been chosen for the building are not even in correlation. Now, if you look at the bird's nest in Beijing, a building's design is intrinsically linked to its materiality. So, that's how it's supposed to be. Rather than making sure a material of your choice is later on utilized on the design, it's better to ensure that we decide on a suitable material and make sure that the design and the material go hand in hand. So, how do we go about making these material choices? When designing buildings, we usually have a choice as to what material to specify. Materials can be compared as being more or less harmful to the environment. We should obviously choose less harmful materials. If you see here, this is the George and Cathy Center for Horticulture in Toronto. If you look at this building over here, you can see there is a combination of open stone facade with glazing and glass facade as well, suitable for the climate that is prevalent there. So, this stone actually helps to create an identity with the site it is resting on, and the glass helps to achieve passive heating and cooling techniques. So, it is very important that we choose a material which is suitable to that site and can be procured within the region of the site. You should opt for materials that use less energy. You should use materials that make our buildings definitely more energy efficient. And finally, it should be both aesthetic as well as enduring. What is considered as a harmful material? If it's number one, toxic to the environment, it either endangers wildlife or removes some kind of habitat, it endangers or compromises local people, processing or manufacturing harms the environment, some materials are limited as resource, and some materials are not as easy to reuse or recycle. Some materials are energy intensive. So, materials can obviously be classified as renewable or non-renewable. Renewable materials include wood, straw, bamboo and other growing substances. Though in this context, I should tell you that wood, even though is considered renewable, in some cases it is considered not good to use because number one, it promotes deforestation and felling of trees, which is not a good thing. And the second thing is, in some countries, in countries like Canada, North America, wood is in abundance. But if you look at countries like India and China, deforestation is the only source of providing wood. So, wood I would not consider a renewable resource, though for all practical and scientific purposes it is considered renewable. Non-renewable materials include metals, stones and items that do not basically keep growing. It is preferable to use renewable materials, but when it is not possible, one can source recycled materials or materials with significant recycled component, such as steel, where a good percentage of the product is actually put back in the manufacture of goods at the end of life, which is nothing but scrap value. Metal, steel and all has a very high scrap value. Reuse materials, which is preferred as it's not necessary to put additional energy into manufacturing the product. Preference is almost always given to the use of more durable, long-lasting materials. It is expensive to have to replace windows, roofing materials as well as cladding. Expense can be measured both in terms of dollars as well as energy. And when I say energy, every element or material has an associated energy element to it along with a greenhouse gas emission. So, if you think of embodied energy, this is what when we say every material has an inherent energy component. So, embodied energy is nothing but the energy associated with harvesting or mining, manufacture, transportation and construction of that material. Transportation energy is significant for all materials, even if they are of the renewable variety. And when I say that, it means if we choose to get some kind of timber that is not locally available, but it has to be procured from thousands of kilometers, then it is in embodied energy of the building substantially goes up. because that material has to be procured using trucks or trains which consume a lot of fuel. Materials with high embodied energy are less desirable from a sustainable perspective. And this is what we need to keep in mind when we construct a building. All the materials that we choose have to have a suitable embodied energy, and we have to keep this embodied energy in mind even when the building is in use, as well as when the building is considered ready for demolition. When we demolish a building, so much of embodied energy is actually lost because every brick has a particular embodied energy. Imagine thousands of bricks, so many wooden columns, beams, concrete, all of that has a set embodied energy, and when we break that down, it's equivalent to consuming all of that embodied energy again. However, some high energy materials are replaceable for certain uses. So, concrete is considered irreplaceable for its thermal mass, aluminium for its durability, and steel for its strength. Relationship between passive design and sustainability. So, passive solar heating and passive ventilation for cooling, assisting in creating a sustainable building by reducing dependency on fossil fuels for heating and cooling buildings, as well as reducing the need for electricity to support lighting by using practices of daylighting in buildings. In LEED, passive design assists in gaining points in the energy and atmosphere category, as well as air quality, as passive design promotes natural ventilation and daylighting strategies. So, we have to make sure that all design buildings are not strongly passive versus all passively designed buildings are not considered very strongly sustainable. So, how do we talk about retaining versus rejecting heat? Materials can be classed as those that retain heat and those that reject heat. Heat retention is useful if we wish to tear the free energy component from the sun in the material. Heat rejection is also called insulation. Insulating materials are used to retard the heat flow through the building envelope. So, depending on what kind of climate our building is in, we have to decide whether we want to retain the heat or we want to reject the heat. And that has to be done in the level of entry itself, because once some kind of heat enters the building, it cannot be sent out, and it's better if we want to retain the heat that we bring in devices to bring in the heat in such a way and that it cannot exit the building at the speed it is entering. And that's what we use our glazing devices for, like we have discussed in the previous presentation. Insulation at a very high is essential in all elements of cold climate building envelope. Thermal bridges are points in the building envelope where there is insulation that is lacking. Thermal bridges are to be avoided as they result in heat loss and normally even degradation of the building envelope at the point of breach. So, when you have a cold climate, you have to ensure that heat is retained really well. So, once you have heat staying into the building, and for some reason insulation materials obviously for practical purposes not a never ending length. They are done in passages and pieces. So, when they are done in these pieces, it has to be ensured that it's continuous, and it cannot be done in such a fashion that there are huge gaps between these, because these gaps are considered thermal bridges where the heat will again escape, and to get it back into the building is not going to be a very easy process. Different ways perform different ways to function of their materiality and thickness. So, if you look at some insulation materials are less environmentally harmful than the others. Here you have the fiberglass bat, and here is the soya bean based spray. So, different types perform in different ways and as a function of their materiality, and more the insulation better it is. But cost is a factor again over here, and we have to see what kind of insulation is healthy and environmental friendly both to the environment and the users as well. Now, if you look at this spray cellulose insulation, this is styrofoam, And you have different R values over here, if you can see. If you look at the R values, it's nothing but the holding capacity of the of bat insulation. So you have 1.5, 2.5, 3 and finally 3.5. So these are the different wall bats and the different R values. Here you have the spray cellulose insulation and this is the rigid fiberglass. Heat storage capacity of materials. The specific heat of materials is different than their ability to store this heat. This is referred to as thermal mass or heat storage capacity. Thermal mass is the ability of a material to hold the heat but slowly release it back into the environment, giving a flywheel effect. So we often have to make a choice depending on the climate of do we need to store the heat to have it released later in the day when the sun is down and the temperature is lowered. So one important thing over here is that's why institutional buildings and all, when you see in hot climates, what happens? It is stone. And institutional buildings, the usage is only in the daytime, morning to evening. By 4 o'clock, the buildings are considered empty. So the stone has a great percentage of absorbing heat. Throughout the day, it makes sure that people are comfortable by absorbing the heat that is supposed to enter the building. And once the students leave in the evenings, it will become very hot inside because it releases. And again by next morning, it is cooled down and it is fresh for the next set of occupants. Similarly, in a cold scenario, the opposite happens, where the heat is actually stored in concrete. Concrete is a very good thermal mass which releases it slowly throughout the day, such that even in the evening, it can help to keep the space warm. Now, looking at the heat storage capacity of various materials, where materials with high thermal mass are helpful in heating of building interiors in cold climates, you need to select materials with high heat storage capacity but that are not conductors. So let's look at water. You have 62.5 BTU, cast iron 54.0, concrete 31.7, glass 27.7. You can see brick is 24, pine is similar to any kind of wood, is 18.1. So here in the topmost column is what these four materials are considered really good, but conductors is not suitable, so cast iron gets cut. So water, concrete and glass. Thermal mass. Exposed concrete floors are becoming increasingly common in sustainable buildings. The concrete is both structural as well as acts as an excellent storage device for storing free solar energy that comes in through most windows. This is Island Wood in Seattle. Thermal mass can be less harmful by replacing some of the cement with content like fly ash, which is considered a waste product of the steel industry. This can also be added as an additional sustainable element. The concrete can be stained with colors if required. So if we look at the thermal mass of concrete as such, it comes to a scenario where it absorbs a lot of heat throughout the day because of the glazed windows, like in this scenario, and a couple of other examples we have seen before. It absorbs the heat, and as the day progresses, it gradually releases the heat even once the sun angle completely changes. So concrete is a very suitable material, and to make concrete a more acceptable material for sustainability, you can add additives like broken clay, ceramic, fly ash, which are all waste products of some other industry. So concrete is both structural in a way, so we have a very good purpose of utilizing it because it's structural as well as has a particular purpose in passive heating, and it helps utilize this free solar energy that comes in through the windows. So some of these, like most people would consider concrete a not very sustainable type of material because of the amount of cement it utilizes. But cement, like we just mentioned, can be replaced with other materials like fly ash, broken ceramic, broken potware, which is a base product of other industries like the steel industry. And for other practical purposes, the concrete can be stained with colors if desired. So if you look at thermal mass as a concept, you have something called water walls that have been used. We have seen that water, concrete and glass have relatively good thermal masses. So, we have to make sure that whatever material that we use, we have to cohesively use it as a passive heating technique or a passive cooling technique for passive design to be successful and to be considered a sustainable design. That brings us to the end of this lecture. Thank you.